Hello, I am Suresh from Infosys, and today we are going to look at another important topic in programming, which is called as data structures. So, data structures is in fact quite a big topic. So, I think following this semester, you will have several courses on data structures. So, to begin with, let us have a quick recap of what we looked at yesterday. We looked at what we call as C preprocessors. So, we saw the introduction to preprocessors, macros, compiler control directives, and some programming examples. So, at the end we were looking at compiler control directives, and we will revisit those cases quickly once again and before we actually get into data structures. This is what we looked at yesterday, that preprocessor is a process which happens before compilation, and if you invoke the compiler, preprocessor is automatically invoked, and there are mechanisms to invoke preprocessor separately. So, these are the directives that we looked at: hash define, hash undefined, include, if def, end if not defined, if else. These were some of the directives that we looked at. In specific, we looked at this particular situations where you have included a file containing some macro definitions, and it is not known whether a particular macro is defined or not, but how does the programmer go ahead and program or put the source code. So, then there are different types of so there is a customer, but he has different types of hardware platforms, hardware and software platforms, and he wants us to develop application which compiles both on both kind or multiple kinds of hardware and software platforms. So, the third situation was similar to the second situation, but here we are developing a program, but that program has to satisfy different criteria or different properties for different users. So, how do you do that? And lastly, this was probably closer to our heart because most of us use print statements for debugging purpose, and once the program becomes error free or a block of program becomes error free, so normally we remove the printf statements. So, in the process we may spoil the structure of the program, in the sense we may alter the control execution, because if there are a lot of nested loops, if there are a lot of nested if then else statements, if in the process of deleting the printf statements we may alter the structure of the control structure of the program. So, how do you control that? So, these were the four situations that we looked at. The first one was fairly simple. You have a macro called if not defined, and the test is the one that you want to define. Okay. So, and you want to define it only if it is not defined earlier. So, you use if not defined test, that is the macro that is the directive that we use. If it is not defined, you are defining it now, hash define test. Okay. So, the first one was fairly simple case. So, the second was you have multiple platforms. For example, in this case I have taken Windows and Unix, and you want when you compile on an IBM machine, you want to include this portion of the code. If you are compiling for a Unix machine, you want to include only this part of the code, and this is how you control. If define IBM PC, do that, otherwise you do this. Okay. So, how do you do that? You can say hash define Windows. So, as soon as the preprocessor looks at this portion of the code is included in the source file or this code, not the both. So, thereby you can control portions of the code which has to be included for a particular hardware software platform. Similar concept can be used for the third situation also. You have a company ABC for which you want these these lines of code which defines the properties or the characteristics of the program, else for all others you want to have this group B code of lines, something similar to the previous case. So, the third one is so typically what we do is we say something like define test. Okay. And everywhere I want to use a printf statement for debugging purpose, I use this hash if def test. So, some people do if def, but that takes out the execution time when you actually compile. Okay. So, you do this if define test, this print statements are executed. Okay, and again if define test, this print statement is executed. You define test as long as you are debugging the program, and once you are done and you know that your program is error free, remove this line, say remove this define test line, recompile the program. So at that time these source codes which are under the class of if def test will not be included in the source code. So thereby your program shrinks and you get the desired results. So with these 4 situations we have learned how to use the compiler directives effectively. As I said, all these compiler directives comes in very handy, especially the first 3 cases comes in very handy when you are developing large programs. When you are developing large programs, there are several common things. There are several reusability. The code that one programmer develops need to be used by somebody else in the team. So thereby those compiler directives, especially the macros and the inclusions of files comes in very handy. I hope you will get some time later in your say course to experiment the things that we have learnt under the compiler directives. So without wasting much time, we will get into the next topic, but before we end that, there are several other preprocessor directives. Some of them are hash error, hash pragma, hash line. So typically no course teaches these things. So once you become a reasonably good C programmer and start developing large programs, lot of manual pages are available for these kind of facilities that are provided in the programming language. You need to go through it, quickly understand and use it effectively. So let us quickly get into data structures. So these are the things that we are going to see. We will have a very brief introduction and we will see what are primitive and non-primitive data structures, and then we will see these 4 data structures: stacks, queues, linked lists and trees. Probably I will reverse this list. I will discuss the linked list first, followed by stacks and queues, and then the trees. Having understood the concept of pointers, you should know that in a program there are a lot of runtime data that can flow in real time programs. So smaller programs are of not much interest. Okay, so you know how to use the heaps. So having known that, we just know that how do we get a block of bytes from the heap. So this topic of data structures will teach you how to organize that data so that this problem solving becomes easy, because you see every problem comes with an associated data, and that associated data will have some relationship in the problem that it is representing. But in the main memory, you know what we have is a random access memory, which is nothing but an array of bytes. So the theory or the concept of how to bring the real life data in whatever form that you have and arrange it in the block of memory, which is an array of bytes, how do you put that and still process the way in which the data is processed in real time or real world. Okay, let us look at that with very simple examples. So data structure is representation of the logical relationship that exists between individual elements of data. Okay, so far we have not discussed what probably the most complex data structure that we have seen so far is arrays, and you know how much limitations that it has. In other words, a data structure is a way of organizing all data items that considers not only the elements stored but also the relationship between each other. Okay. So because of its importance, the data structure that you design actually affects both the structure as well as the functional aspects of the program that you write. So that is why many people try to put this program that you write is nothing but algorithm plus the data structure, because for the same algorithm you can have multiple data structures that captures the data that you want. Okay, both the algorithm and data structure will have a strong influence on how good your program is. And again, at this point of time, I would like to warn, or I would like to advise that there is no single data structure that you can say is best data structure for every application. So each application has its own characteristics, and you may have to design a data structure or tune the existing data structures to meet the requirements of that particular problem. So there is no single solution for data structures. So, every problem will require a data structure which is probably different from the ones that you already have, some small tweaks. Having said that, I should also tell that there are many problems which straight away takes the data structures that we define or that we know of and does the problem very efficiently. You know that an algorithm is a step-by-step procedure to solve a particular function. That means algorithm is a set of instructions written to carry out certain tasks, and the data structure is the way of organizing the data to see that those tasks are done efficiently by maintaining the logical relationship between the elements. To develop a program for an algorithm, we should select an appropriate data structure for that algorithm. So, please remember. So, therefore, algorithm and its associated data structures constitutes what we call as a program. Now, let us quickly look at some of the fundamentals or the fundamental classification of data structures. They are normally divided into two broad categories. So, fundamentally only a bit and a byte can be called as the machine data structure, because machine can understand only ones and zeros, it can understand a bit, it can understand a byte, probably it can understand an integer or a floating point in current day machines. Okay. So, the remaining data structures are generally classified as primitive data structures and non-primitive data structures. We will see what are those quickly. So, data structures itself can be broadly classified as primitive data structures and non-primitive data structures. Under the classification of primitive data structures, we have integers, float, character, pointers. There may be few more things. Okay. Under the classification of non-primitive data structures, you have basically lists, you have linear lists and non-linear lists. In the linear list, we have arrays, linked lists, tags and queues, which we are going to see. Arrays is the one that you have already seen. Under the classification of non-linear lists, there are graphs and trees. We will quickly look at both of them. So, what are primitive data structures? So, these are basic structures and directly operated upon by the machine instruction. That is exactly what I told. Machine can understand bits, bytes. Some of the modern day machines can understand what an integer is, because integer is typically about 4 bytes or 8 bytes depending on the machine. Similarly, it can understand floating point numbers. Similarly, their arithmetic and all gets implemented in the hardware. Okay. So, so, when somebody asks you what is primitive data structures, you should say those are the data structures that can be directly operated on by the machine instructions. In general, there are different representation for on different computers. The same integers are represented in different forms in different machines. So, primarily they are represented using two forms, the little Indian format and the big Indian format. I hope you have learnt it. So, if not, you will learn it very soon. So, then you have floating point, you have single precision representation, you have a double precision representation, character constants, string constants, pointers, etc., all fall under the category of primitive data structures, because the machines can understand, you can operate on that directly using machine instructions. So, the non-primitive data structures are generally slightly sophisticated data structures. So, these are derived from primitive data structures. Basically, the components of non-primitive data structures are basically primitive data structures. The non-primitive data structures emphasize on structuring of a group of homogeneous and in some cases heterogeneous data items. That means, it could be a collection of integers, it could be a collection of characters, it could be a collection of floating point numbers, it could be a collection of arrays, sometimes it could be a collection of integers and floating points or something else. So, basically these non-primitive data structures are generally a collection of data items, okay, and in most cases it will be homogeneous in type, but that does not mean that it will always be homogeneous. It can accommodate heterogeneous data items as well. But for most of this session, we will look at only homogeneous data structures. So, some of the non-primitive data structures are lists, queues, stacks, trees, graphs. These are examples of non-primitive data structures. The design of an efficient data structure must take into consideration the operations that needs to be performed on the data. Do we need to search on the data? Do we want to do some processing on the data? Do you want to cut that data into multiple pieces? Do you want to merge different data structures of the same type into one? These are some of the operations that you would do on data. So, you should look at the data, the data as well as the operation that is required in the problem to be done on that data. So, this will define what an efficient data structure is. Some of the commonly used operation on the data structure can be broadly classified or categorized into this. You need to create the data structure, you need to select one data item in the data structure, you need to update a data item in the data structure, you need to search, you need to sort, you need to merge, and ultimately when you are done with the job, just like when we talked about heap memory, we need to delete it or we need to free those data structures. So, quickly we will see one data structure that you have already seen. Okay. So, arrays, and we will quickly see the limitations of that, and then we will jump into the other data structures. So, it is statically declared, size to be known at compile time, allocated in a contiguous space in main memory. That is its huge advantage, because having allocated on contiguous space, any element can be accessed using an index, typically a of I. Size cannot be stretched or shrunk while running. So, that is the drawback of arrays, and unutilized space in the array goes waste and hogs the memory. So, some of the problems here or some of the limitations here can be addressed using dynamic allocation, but that will not solve all the problems. Okay. So, you have the linear structure here and you have some beautiful properties in arrays, but what are those? What are the operations that are efficient on arrays? If I want to access an element, I know if I know the index, I can access by that. If I want to search, what do? You start from the first index and go on looking at until you get the element or you exhaust the array, or you can do that in the reverse order. This also looks reasonably okay, if the array is small. But let us look at some operation that would probably create a problem. Suppose I want to insert a new element into the array. You already have an existing array and you want to insert a new element. So, what should you do? So, after the new element gets into it, starting from that index till the last index, you are supposed to move all the data elements, you want to shift all the data elements to the right for the insertion to happen properly. So, if it is a reasonably big array, the number of shift operation that you need to do could be very large, and that could be inefficient. The same situation happens when you are deleting an item. Assume that you are deleting the first element in the array. So, what should happen? So, what was in the second element should now come to the first element, what was in third should come to the second element, and so on. This will also involve a lot of operations. Okay. So, probably only if you want to delete the last element, there is no extra operation that you need to do. Similarly, if you want to insert at the last after the last element in the current array, there will be no extra instructions or extra operations. All other things makes insertion and deletion operation in an array very inefficient. So, some of the other operation is merging of arrays and all. So, insertion and deletion, the inefficiency of arrays in supporting insertion and deletion operation is itself a case for us to look at other data structures which perform better on this. Okay. So, the first thing that we look at is linked list, which primarily addresses the drawbacks of arrays. A linked list consists of a sequence of nodes. We are introducing something called as node. Those are nodes, and what is it? Each node contains a value, and contains what we call as next element. See, A, B, C, D are the values, and a link or pointer to the next node is that. Look at how neatly the data structure is organized. So, each data is kept in a shell called as a node. The data itself occupies the portion of that, and there is an address, there is a pointer field which points to a node which is similar to the current one, which is following this node. So, you have A followed by B followed by C followed by D. The last node contains a special value in its address field, and that is called as null pointer or a null link. Okay, so I hope you have understood how the data is organized here. So you can have the information of the first element in a name called head, or you can also name it as my list. Some data structures or a variation of linked list can also maintain a pointer or a value which holds the address of the last element to make some operation easy. Okay. So now, so what is a linked list? It is a sequence of nodes. What is a node? A node is a data structure which has two components, the value component and the next address or the next element component. Okay. So the linked list basically is a sequence, it dictates the order, what is the first element, what is the next element, and so on. So the last element does not have any node following it, so you put a special value to the link field or the next element field, which is called as null link. Now let us quickly look at some of the terminologies in linked list as well as some of the operation. A node successor is the next node in the sequence. A's successor is B, B's successor is C, C's successor is D. The last node has no successors. Similarly, there is a terminology called as predecessor. A does not have any predecessors, B has a predecessor as A, or B is predecessor of C, C is predecessor of D. Okay. So, successor and predecessor. The number of elements in the linked list is generally called as length of the list. So, why this is important is in arrays the length of the array is determined in statically during compile time. So, if you see here, to begin with you will start with an empty list. Whenever a new element has to be added, you use malloc to get a node, put the value that you want into the value field, and then take that node and do the insert it, or you place it wherever you want. Okay. So, linked list is a dynamically allocation or a dynamically allocated storage data structure. Okay. So, one of the first operation that we look at is parsing. So, we looked at arrays. How do you parse an array? You start with an index 0, go up to the last element. Similarly, you can do the reverse. So, in linked list there is only one way you can look at all the elements in a sequence, that is starting from head. Head contains the value or the address of the first node. So, then you now access A. So, now what I will do is I will copy the head value into P. This is P is just a temporary variable. So, initially it points to head, you read that, and then you move that. How do you move to that B? So, P gets the value that is stored here, the next element portion of the node A, you copy it to P. So, now P points to B, and now you go on doing that until you get the last element. So, that is what we call as parsing. Parsing is a process where you look at every element in the list in some order. So, you should make it efficient, that is all. Let us look at the insert operation. You remember insert operation created some inefficiency in arrays. Primarily, you need to push all the elements from the index where you are inserting until the last element to the right by 1. So, it requires some number of shift operation. If the array is big or if the list is big, this could lead to great inefficiency. So, let us see what will happen in an insert operation in a linked list. So, the first step is search B. So, you are supposed to insert after location B, after the element B, you are supposed to insert a value containing Z. Okay. So, search B starting from head. So, what do? You have a temporary variable called P, copy the value of head into it, check the first node, see whether it is B, it is not. Use the next element field of A, get the pointer of that and go to the next successor node and see it, you got B. So, you got B. So, now you are supposed to insert the new element after this. At this point of time you create that new node. How do you create? You know malloc. You malloc that many bytes, you have the pointer to Z now. Okay. So, what do? Look at the sequence of step. I know the node following which Z should appear now. I also have the pointer of or the address of z. So, the first step that I do is I will take what is there here, the pointer, the value of this pointer here, and make a copy onto this. Initially it will be null, so I make a copy out of this. So, what is happening now? The next element of B is pointing to C, the next element field of Z is also pointing to C. That means I know this address. Now, what do I do is I take this, I take the pointer to Z and put it here. Okay, I get that. So, that becomes the list now. A is followed by B, B is followed by Z, Z is followed by C. The sequence of operation, let us rubric it once again. So, I got P and then I got a malloc to Z. The first thing that I need is I change this address. So, the address element of the next element of the new node gets the value of P dot or what is there here. Okay, you copy it, duplicate, and then you modify this with the address of this. So, you are done. So, the sequence of operation is very important. Anyway, we are not going to implement this in C because there is a separate course on data structures probably in your following semester, where you will have to do all these things probably in C or C++. So, when you want to delete, the process is approximately the same, but there are some complexities that can come in here. So, what do? The first step is same. I need to search for the element that needs to be deleted. Same thing, I open a variable pointer P, copy head value into it and go on searching until I get C. Now, I want to delete this C. So, what do? I need to do that. Okay. So, remember that you know the pointer to the node that has to be deleted. So, you take the predecessor of that, change the address field of that with the address field of this. That means, copy this field into this. This element goes free. Now, I have pointer P, pointer to C. I need to free this. Please remember, okay, you need to free this so that you don't hog the space in heap. Okay. So, the delete operation is fairly simple. So, you looked at insert operation and the delete operation, which were inefficient in arrays. So, we looked at parsing in linked list, we looked at insertion and deletion in linked list, all looked very efficient. And to begin with, linked list is not statically declared, it is dynamically created. So, it is primarily addressing all the problems that arrays had, but arrays had one beautiful property of random access. You could access any element using A of I. Here, if you want to access an element, there is no way. You need to start from head, go on until you find the element or find the node that you want. So, that is a major drawback in linked list, but in all other aspects, so linked list seems to be better than arrays. Okay, but still people use arrays because for a small list it is all right even if you waste some little space, but arrays provides you beautiful way of accessing the elements like A of I. But so some of the seasoned programmers will implement arrays using the pointers, which we have seen in last few sessions. So, both gives very efficient access. Linked list does not provide you efficient access, but some of the operations are efficient, especially the insertion and deletion operations. So, generally data structures are encapsulated and abstracted as abstract data structures. So, if you look at linked list abstract data type, it has these functions: create, delete, search, insert, delete, add, append, length. So, I think the names itself indicate what is supposed to do. We will not discuss this much because you are not going to implement this. If you know what a linked list, what are its advantages compared to arrays, and what are the operation on which, what are the operations which are efficient on linked list. So, that should be good enough for you to understand what a linked list is. So, some variations of linked list exist: singly linked list, doubly linked list, single circular linked list, doubly circular linked list. So, all these things probably you will study later. Having looked at one data structures, we will look at the second data structures, which are called as stacks. So, please remember that we are looking at non-primitive data structures. Non-primitive data structures are basically a collection of data items. Generally, they are of homogeneous type, but in some special cases it can be heterogeneous. So, stack is also a collection of data items of same type. It is a homogeneous data structure, it is a collection. Okay. It is an ordered collection of elements. So, linked list was also an ordered collection. Arrays was also an ordered collection. But you see the difference, linked lists and arrays differ by so much. So, one is statically allocated, one is dynamically allocated, one is random access, one is sequential access. So, stack is now another data structure which captures ordered elements in a different form. So, what it is we will see. We have been referring to stack earlier as well. So, but here we will see and characterize that. So, the ordered collection of elements which are called as a stack here has a special feature that is deletion and insertion of the elements can be done only from one end, which is called as top of the stack. Due to this property, because you can put and remove the elements from only one end, it will primarily implement an order called last in first out order. Okay. So, that we will quickly see how it is done. So, it could be thought of just like a stack of plates on a table in a party. So, what happens in a party? They would have kept the dining plates one above the other. A guest always pick the top of the table, the plate which is on the top. Okay. So, when the waiters put the plates on the rack or on the stack, they will put on the top. So, if a waiter has put some plates, what would be the first plate that the guest picks up? It would be the last plate that the waiter would have put in. So, the last in is the element that comes out first. Okay. It is a non-primitive data structures. When an element is inserted into a stack or removed from the stack, its base remains fixed, whereas the top of the stack changes. So, that you will understand better with a figure. Okay. So, just imagine this data structure like an open bucket. So, there is no top to this and there is a bucket which has a bottom. So, this has a fixed bottom, only the top varies. For example, the top here is this, the top element is here, the first line. So, if I remove this, so the top becomes this. So, the top is moving up and down. So, when you push it goes up, when you pop it goes down, and bottom of the stack remains the same. So, this is something that you have seen in program layout when functions are called. So, a stack frame is allocated with respect to each function call, the local variables are put or allocated into it. So, when the function returns, what is the stack frame which when there is a return statement, what is the stack frame that gets knocked off or that gets deleted from the stack? It is the last function that was called. So, the last function will be removed when a return executes the last function that was called, that stack frame will go off. So, you have already seen that, but we are trying to characterize that. So, the insertion of element into the stack is generally called as push, and deletion of element from stack is called as pop, and both these operations happen only at the one end, which is called as the top end. So, push goes here, the arrow mark is slightly wrong there. So, push puts the element into the stack, pop will remove the element from the stack. So, these are some of the functions that you can imagine on the stack. You need to create a stack. So, when you create a stack, a space is allocated and nothing is there in the stack, bottom is fixed, top is also fixed. So, as the insertion and deletion operation happens, the top goes up, the bottom remains where it is. So, you have create, you have delete, removing the stack completely, you have push, pop and pick. So, the difference between pop and pick is pop actually removes an item from the stack. Pick will just tell you what is there on the top of stack, it will not remove, it will just read what is there on the top of stack. Okay, whereas pop will actually remove what is there on the top of stack. So, similarly, you can see you can have probably a count number of elements in the stack is empty, whether the stack is empty, whether the stack is full, because stack is generally of limited size or fixed size. So, you need to check E is full and E is empty. These two functions, E is empty and E is full, because you cannot pop from an empty stack. Similarly, you cannot push into a full stack. So, there is a reason behind these methods to be made available to the programmer. Okay. We will quickly see some of the applications of stacks. So, to check that every right brace or a bracket has a left corresponding left, every left parenthesis has a corresponding right parenthesis. Okay. Example, this is legal, a match is there between these two parentheses, there is a match between these two parentheses, this is legal, whereas this is illegal. Though the number of braces are same, they are not ordered the same, this is illegal. So, how do you do? So, every left parenthesis you push onto the stack, every left parenthesis that you see when you are seeing the string from left to right, you push onto the stack. Every right parenthesis or the right brace you see, you pop from the stack. So, the character that you are seeing would be either either the right parenthesis or the right brace. The character that you should see after popping should match. You go on until you empty the string and the stack is empty. You empty the string, but the stack is not empty, means that it is illegal. You empty the stack, but you encounter another left parenthesis or a right parenthesis, but your stack is empty, there is an error. So, for a well formed parenthesis, you need to have the stack being empty and the string to be read fully. That is one of the major application, very easy to imagine. So, make an empty stack, read characters until the end of file. If the character is an opening symbol, that means left parenthesis or the left braces, push it onto the stack. If it is closing symbol, that means the right parenthesis or the right brace, and then the stack is empty, report an error. Otherwise, pop the stack, compare the symbol that you have popped and the symbol that you are reading, and then report an error if they mismatch. At the end of file, if the stack is not empty, it is an error. That means there were some extra characters. So, report an error. So, very easy and straightforward example of stacks. There are many other applications of stacks. Calculate 4.99 into some expression. So, you need to know the precedence rules. So, you need to know that this multiplication and this multiplication should happen first, then the addition operation, and within this addition operation it is left to right, this one followed by this one. Instead, what most compilers do is it will convert this infix expression into what is called as postfix expression. It is also called as reverse Polish. So, it is something like this. See, look at this 4.99 space 1.06 space star space 5.99 and so on. So, this is what we call as Polish notation or postfix expression. There is an algorithm to convert this infix notation into postfix, which you will see in data structures sometime in your next semesters. Okay. So, this is what we call as postfix notation, and all compilers do this. So, they will convert this infix to this. There is a very efficient algorithm to convert this. Okay. So, now when you are given a Polish expression, it is very easy to compute or evaluate using a stack. Okay. What do you do? When a number is seen, it is pushed onto the stack. So, 4.99 push onto the stack, 1.06 push onto the stack. When you see an operator, the operator is applied to the two numbers that are popped from the stack. So, once you see this star, you pop and you pop once again and apply that multiplication operation to the two numbers that you have popped up, that is 1.06 multiplied by 4.99. Next, what do? You push the result back to the stack. So, 4.99, the product of 4.99 and 1.06 will go on to the stack. Then you see 5.99, that will go on to the stack. Then you perform this addition operation, 5.99 plus 4.99 into 0.06, 1.06. Then you push 6.99, push 1.06, multiply this one, and you have to perform the operation. So, this entire expression and this expression has to be added. So, you get the desired results. Okay. So, I urge you to practice this. Just imagine a stack or write a stack and apply these steps. Okay. I urge you to practice this to understand it more clear. If you look at this there is another example here, 6523 plus 8 star. So what do? Let me just quickly do this. So what do I do this? So I start with an empty stack. I see a number, I push. I see a number, I push. Then what do I see? I see another number, I push. I see another number, I push. Okay. So then I have the plus. Okay. And then let me quickly write down that multiply plus 3 and then plus star if I am not wrong. Okay. Let me quickly do this. So plus, what do? I pop these two numbers, 3 plus 2, what do you get? I get 5. So 6, 5, 5. I push that back to the stack. Then what do I see? I see the number 8. Then I see star. What do? 8 multiplied by 5 is 40. So 40 is pushed onto the stack. Okay. Then what do I see? I see a plus. 40 plus 5, that is 45. So 45 gets onto the stack. Then what do I see? I see a 3. I push onto the stack. Then I see plus. So 45 plus 3, it becomes 48. Then lastly 48 into 6, so that is applied onto these two. So what goes here is 48 into 6. You get your answer. Okay. So very easy. So once you have the postfix notation, if you see, I am seeing this string from left to right only once. That's why we call it as O of n. So let us not bother too much about it. I need not see the list. I am seeing this strings, that is Polish expression 6523 plus and so on, only once from left to right. The stack can be implemented. Implementation means how do you take this philosophy, how do you take this concept of stack and write a C code equivalent to that. Okay, that is what we call as implementation. So stacks can be implemented using arrays and using pointers as well. So having looked at stacks, we will quickly look at queues. So everybody knows what a queue is. It's basically a list, an ordered list. It's a first in first out. It's a linear list. So you have two specific ends, which is called as the front end and the rear end. The deletion happens at the front end, the insertion happens at the rear end. So that is the difference between stack and queues. So just imagine the queue in front of a railway, a ticket counter, or when you go and collect your hall tickets, or when you go and collect some items, you queue up. So that is the philosophy. So very quickly, that's how the queue looks. So you have something called as front end, you have something called as rear end. From the front end, you are removing the elements. Removing elements are called as dequeues. It is the last, the new elements come in at the last, or from the rear end, we call that as enqueue. Okay. So if you want to dequeue, that's what happens. So the first element goes out and the front moves to the next element. So whereas in the real counter, the person actually moves, you can interpret that in different way. So when you are enqueuing, so the last element goes into the rear end of the queue. Okay. There are some error conditions. So just like stacks, queues are of limited size. If you are trying to enqueue into a queue which is already full, it's an error condition. Similarly, if you are trying to remove something from the queue when the queue is empty, you have an error condition. So there are several applications for queues. All scheduling problems that you know, queues play a significant role. Okay. Suppose you want to schedule schedule the jobs that comes into the computer for execution. You want to schedule it. So typically you will put them into a queue and then take it one by one, or the CPU will take it one by one and runs that program. So similarly, you have priority queues. If you want to have some priority between the elements, you should have multiple queues, and you process the elements in the queue with the highest priority first. So all of you must have used the printers in your laboratories. So what do? You will be sitting in some remote machine and issuing a print command. So the print server sitting somewhere has a algorithm called as spooler, so which will basically take the file that you have asked it to print and queue it up, because printer is a slower device. Okay, so all the jobs gets queued up and you print. So imagine any scheduling problem, the queues have a role to play there. Apart from that, it can also be used to order certain things in a first in first out fashion. So wherever you need FIFO or extensions of FIFO, you need to have queues. So it's just like stacks, queue can also be implemented using arrays. It can also be implemented using pointers. If you use arrays, it becomes static implementation. If you use pointers, it becomes dynamic implementation. So these are some of the functions that you want to exist in queue data structure. So create, delete, is empty, is full, count, enqueue, dequeue. You can also visualize some other special operation, but these are the fundamental operations that you want in queues. Lastly, we will see data structures, graphs and trees. So though the curriculum says that you need to understand trees, graphs, if you understand the graphs, tree is a special case of graph. So that's why we will quickly see what a graph is, and then we look at what a tree is. Everybody knows. Let's not bother too much. Everybody has seen, has learned geography, have learned chemistry, have learned some of the engineering sciences. In geography, you have maps. Everybody is, know Google Maps. So how does a Google map look? If you visualize, how does it look? You have some locations and you have some connections between those locations. So graph is nothing but a mathematical structure. It's a non-linear data structure, so which contains a set of vertices and a set of edges. In the Google map, you just assume the locations as set of vertices, edges or the roads or the links that connect these locations as edges. So that is the structure for graphs. Don't bother too much about formal definitions. It's a collection of two sets. A set which is called as vertices, a set which is called as edges. And what is an edge? Edge is basically a link between two vertices, or two members of V is connected through an edge. An edge connects a pair of vertices, and many have weights such as length, cost and another measuring instrument for according to the graph. So vertices on the graph are shown as point or circles, and edges are shown as arcs or line segments. So very quickly we will see that. These are examples of a graph. These are the vertices that we are referring to, these are edges, and as I mentioned, some of the edges can have some weights associated to that. So typically that weights may be the cost for us to travel from location V1 to location V3, or it could be the time taken, or it could be the length of this distance. It can represent anything. So once you associate a number to the edge, we call it as weighted graph. So this is an application. So this is an example where there are no directions to the edges, there are no weights associated to the edges. This is a simple undirected graph. When somebody says what a graph, they are basically referring to this. If you add some special properties to the graph, it becomes this. You can add only directions, it becomes directed graph. You can add only weights, it becomes weighted graph. You can add both, you get directed and weighted graphs. Okay, remember that this is the fundamental data structure. Okay, see, if I want to list the elements in this graph, it could be V1, V2, V5, V4, V3. It could be V1, V3, V4, V5, V6. There is no order to this. That's why it is called as non-linear or unordered list. So there is a list of vertices, but there is no order to it. But there is definitely a relationship. V1 and V2 are neighboring to each other. V1 and V3 are neighbors to each other. Similarly here, there is some relationship between the elements, but it is not a linear relationship. It is a non-linear relationship. So the graphs are the first example that we study under non-linear data structures. So trees can be defined as a finite set of data items. If you look at this, so you have several paths like this. So there are several, starting from V1, you can go to V2, V4, V3, V1. So in trees what happens is you cannot get any such cycles. So, trees are also called as acyclic graphs. So, let us quickly see that. So, this is one example of the tree, this is one example of the tree, these are the other examples. A tree is a connected acyclic undirected graph. Okay. So, there are some special trees where a single node is identified as a special node and we call it as root. Such kind of trees are called as rooted trees. So, in such case, in such trees there is one node which is called as root, all the other elements are non-root, but there are one set of nodes which are, say for example, in this example 8 does not have any element following it. So, these are called as leaves. You have root, there is only one root, you have leaves 2, 8, 12, 11, 6, 4, these are called as leaf nodes. The rest are all called intermediate nodes. So, this is another example for the rooted trees. So, there is a special type of tree where every node has only 2 children following it. Okay. For example, this. So, you see you have only 2 nodes. So, here you have only 2 or 1, at most 2 children. So, this is an example for binary tree, whereas here if you see root has 3 children, it is not a binary tree. So, here it can be 0 children or 1 child or 2 child. So, this is an example for binary tree. If every node has exactly 2 child except the leaf nodes, it is called as balanced binary tree. Okay. So, these are the types of graph. You can have directed trees, you have undirected trees, weighted trees, and you have some special trees called as search trees. So, these are called as binary trees, breadth first tree, depth first search tree, balanced tree, AVL trees. These are all for databases. Application of trees. The data representation in processing. So, if you want to represent networks, if you want to represent relationships, imagine Facebook. Okay. Imagine Facebook, imagine LinkedIn, you have groups there. So, Facebook is a collection of lot of users, but there are some groups within it. So, to represent that, Facebook uses the network data structure, the graph data structure. So, in networks, if you want to do routing of messages from one computer to the other computer, if you want to classify, so these are the places where trees are extensively used. Trees are also used to build special data structures to make search efficient. So, all the other applications, Facebook, Google, Gmail, all other internet, all use trees to represent, to perform a search. So, the compilers also build trees called as syntax trees, which will make the compiler to process and see whether a sentence or a line in a source program is syntactically correct. Okay. So, those trees are called as syntax trees. In databases, people use tree structures to see certain operations are captured or done efficiently. So, you have trees in databases as well. Trees are also used extensively in coding theory. If you want to encode some messages, if you want to come out with some coding structures, so trees are used. If you want to develop some coding for compression, we use trees. Similarly, cryptography. So, cryptography is a science where a message is taken, jumbled up using some mathematical means, so that it becomes ununderstandable, okay, and then you send it to the receiver and receiver will reassemble it back. So, in order to do the jumbling, which jumbling is the process which we call as encryption, unjumbling is called as decryption. In both cases, trees are used extensively. So, to conclude, we had about 5 sessions with me. It was pleasure for me to talk to you. I hope we will see sometime soon, probably revisiting the same concepts, or probably taking or looking at some other concepts in computer science. So, what we together try to do or try to learn is pointers in C and its applications and use, compiler directives and its use, and we also looked at introduction to data structures without bothering too much about how to implement that in C. Okay. So, as I said, in future courses you will have several topics that will fork out from these concepts. So, you will have software engineering, which is probably an implication of compiler directives. You will have data structures and algorithms and analysis of algorithms, which is a fork out of data structures, and you will probably learn C++ and other programming languages, where the pain of pointers will be removed and the effect of pointers will still remain, but in a more elegant way, which is easy to program. So, with this we will conclude. Thank you very much.